In this lesson, we're going to be talking about IP fragmentation. One of the core functions of the Internet Protocol is to manage fragmentation. What that means is that we've got a discrepancy between the size of the data that we can send and the size that the physical networking medium will accept. So, for example, Ethernet will take 1500 bytes, and that includes headers. We can send 64K bytes through an IP packet. Obviously, there's some size difference, and what ends up happening is that the IP datagram or IP packet ends up getting fragmented. And we can take a look at some information here. Just going to do a quick packet capture, and we can see some messages. We've got IP, and you can see that we've got no flag set, there's no fragment offset, and we've just got messages that are going. So there's actually no fragmentation going on here that we've seen so far. So just to demonstrate the concept, I'm actually going to send some messages that are going to have to be fragmented. And I'm going to do that by specifying that the size of each packet is going to be too big to send out on the wire. So I'm going to send this to my local network router or my default router. You can see 3,108 bytes are going, and that's because I specified the size as 3,100, and we've got to add on additional bytes for the extra headers. Let me kill that, and now we can go back and look at the Wireshark capture. Let's just pull up an ICMP filter here. You can see there are 3 fragments here. Frame 448, 449, and 450 are all fragments. So let me clear this out because we're not actually seeing the fragments because we don't know just from the fragment what we're actually looking at here. Once we've put it together, we figure out what's actually going on here. What we've got here is a fragmented packet. You can see where the flags say more fragments, and in this case, the fragment offset is 0. You may be wondering how the receiver knows that all of those packets belong together. Well, take a look at the IP identification field here. It's 54511. And we've got another message here that should be a fragment of the same one. We've also got 54511, and the fragment offset is 1480. We've already taken 1,480 bytes, so we're going to slot this one into 1,480 because we start counting at 0. That 1480 bytes went into slots 0 to 1479. We're going to slot the first byte of this fragment here into slot 1480. And we've got the last one here again. The IP identification field says 54511, and we've got a fragment offset of 2960, which we would expect because we've got 1480 from the 2 packets that were ahead of it. Because of that, we're now slotting into offset 2960. So I specified 1500, we only got 1480 in each one, and that's because of 20 bytes of header. So we only had 1480 bytes of actual data when it got to the other end because we pulled the header off, and so that's where we end up with 1480. But you can see the way that we reassemble these in IP is the IP ID here will actually tell us that these 3 packets belong together. We've got these 3 with the same IP ID. The offset, of course, is different because we've got a chunk of data and then a second chunk of data and then a third chunk of data. And every one of those, of course, increments the byte size. And so we've got to be able to slot them into the appropriate place. Again, one of the critical functions of the Internet Protocol is to be able to handle fragmentation. We can see here, using these large-sized echo requests, that we end up doing fragments based on the maximum transmission unit of the underlying networking protocol. In this case, it would be Ethernet. And again, the MTU of Ethernet is 1500 bytes. You can see again that we've got these fragmented packets, and that's really one of the core functions of IP. And to put them back together, we need the IP ID and, of course, the fragment offset.